Hello everyone. Welcome back to Palance AI and welcome back to the Deep Learning Foundation series. In the previous video, we saw how convolution operations work, how filters slide over an image to detect localized patterns. But here is the next natural question. Once a CNN extracts all these features, how does it simplify them without losing what actually matters? That's where pooling layers come in. In this video, we'll build on everything we've already seen, the convolutions, and further understand what are these pooling layers and what exactly they do. And also, what about the weights when it comes to convolution layers and also the pooling layers? We're going to learn all about that in this video. This video is again part of my Deep Learning Foundation series. If you're new here or want a stronger intuition, I have linked the full playlist below, including the earlier videos on deep learning intuition and also convolutions. Please check them out. All right, let's dive in and understand pooling layers in detail. So what are pooling layers? So pooling layers are something similar to the convolution operation, but the operation itself is different. Okay, let me again take a hypothetical, simple 6x6 2D grayscale image. Okay, again, there's no depth grayscale. So we're gonna use a pool size. So pooling layer, you also do it something called, again, you do with the windows or filters or kernels, right? But typically we use the term pool size. So pooling filter, if it helps, think of it as a pooling filter. So pooling filter is also, let's say, typically use 2x2, but let's say we use a 3x3. Just I want to show you, compare it with similarly to what we have been doing with the regular convolutional filters. So we're going to use a pooling filter. Okay, of 3x3. What is this going to do? So same thing, you're going to take this pooling filter and put it over the original portion, original input image. But the difference is in the operation. If it was a convolutional filter, you're going to do element-wise multiplication of each element in the filter with the corresponding value in the original input image, and you sum it all up, right? That's what the convolutional filter does. But for a pooling layer with pooling filters, you simply take the maximum value here, because there is nothing here in the pooling size. There is no values in the pooling filter. You just put this window there, and whatever the maximum in this area, you take that. So what is the maximum here in all these values? 0.7, right? You can see 0.7 is the max value. Okay, so that's my value. Okay, and I'm going to put it there. Then I'm going to slide my pooling filter a little bit. Okay, and then I'm going to look at the maximum value again. You see the 0.7, so I'm going to put it there. I'm going to slide again. What is the max value now? It's 0.9. I'm going to put the 0.9 here. You got the idea. So as I slide this pooling filter over my entire input image, I'm going to fill all these values like this. That's pooling layer. Okay. The difference between the convolutional filter and pooling filter is, in convolutional filter, you do element-wise multiplication of each value in the filter with the corresponding portion in the input image, and you sum that up. But for the pooling, like let's say max pooling, right? You calculate the maximum value. Okay. Now, is that the only way to do pooling? No. So there are different types of pooling. You can do max pooling, which is what I just explained to you. Or you can also do an average pooling. So for example, you put this window here, right? And so instead of just taking 0.9, just sum up all this and take the average value. Just take the average value, and that would be average pooling. In practice though, max pooling is more preferred than average pooling, because again, you want to capture by taking a maximum value, you're getting more informative of that particular pixel. So typically you prefer max pooling over average pooling. All right. So this is just to make you understand how pooling operation is different than the convolutional operation. Okay. But putting it all together, right? Again, you take a 3D input image. It's a 32 by 32 by 3, right? 3 channels. And then you apply. Now, first I'm going to show you with a convolutional filter, so that I want you to see the difference between a pooling filter and convolutional filter. So let's say we're applying a regular convolutional filter like I explained in the previous slide. So it's a regular convolutional filter. It's not a pooling filter, okay? So you take the regular convolutional filter, 3 by 3 by 3, right? Again, the depth of the convolutional filter will be the same as the input channel, okay? So you're going to slide it over the input image, right? And then let's say if you have 10 filters, this is how your output shape is going to look, right? The 2D shape is going to shrink a little bit from 32. Again, I'm not using any padding or any strides, just a normal convolutional operation here. And this is what the output looks like for a regular convolutional operation. Okay. Now let's contrast this with, again, this is the convolutional layer. So let's contrast this with a pooling operation. So let's say you have a pooling layer. So after the input layer, you have a convolutional layer, the regular convolutional layer, which I explained to you. After convolutional layer, let's say we have a pooling layer. Okay. So this is a pooling layer in blue. So what happens? Now you take a pooling filter. One main difference, as I already explained, one of the things I already explained, right? What happens with the pooling operation compared to a regular convolutional operation. Another thing is, see, because pooling is just taking the maximum value here, the pooling filter, there is no depth to that. Pooling filter is just 2D. Okay, so you just take a 2D pooling filter and you typically use the pooling size. Okay, 3 by 3. Just take this 2D pooling filter and put it on the original input, the 3D input image, and but because you're just using a 2D pooling filter, right? You're just going to put it on the surface, on the 2D shape, okay, like this. That's another big difference. So if it was a convolutional filter, remember, if it was a convolutional filter, your convolutional filter, the depth would match the depth of the input channel. Whereas for pooling size, it's not the case. It's just a 2D pooling filter. You take the 2D pooling filter, put it here, take the maximum value, you'll get one single value, scroll this pooling filter over the entire 2D shape, the first 2D shape here, you're going to get a new output 2D shape, new 2D output shape. So similarly, something like this. So you see, so there is no there is no depth here. You just take a pooling filter and you do the pooling operation over each 2D surface in your original input, right? Not the original input, in the input, right? For example, we're applying the pooling operation to the output of the convolutional layer. So you take the pooling filter, put it here, do the pooling operation over this surface, you're going to get one new output shape, 2D output shape, right? Similarly, keep doing the pooling over the entire depth of your, over the entire depth, and you're going to get a completely new 3D output shape, and the size is going to look like this. Okay, so hopefully this is helping you understand, the difference between pooling layer and a convolution layer. Pooling layer, again, we use typically to downsize the image. I mean, when we typically combine with strides, and generally we use a pooling size of 2 by 2. I mean, there's no limit. You can use whatever the pooling size you want, but typically people use, practitioners use 2 by 2 pooling sizes. Okay. The formulas are again pretty much the same. There is no difference. Whatever the formula we use for the convolutional operations to determine the output shape. So these formulas are for the output shape. So for no padding, this is the formula. If you pad, this is the formula. So these formulas I'm showing for the pooling layer, they are the same as for the convolutional layer. But hopefully you understand the concept here. The pooling layer, typically either they take the max value of the kernel or filter, or the average value, depending upon you're doing max pooling or average pooling, right? And another thing is, for the pooling, there is no depth here for the pooling filter. You just do a 2D pooling operation. Okay. And the output, final output shape after the pooling operation, that depth is going to match with your original input, whatever that input you're using, to do the pooling operation, and that depth will match. Okay, so this is in brief about pooling operation. Next, finally, we're just going to look at this weights or parameters. Okay, so again, the weights are the values of the filter or parameters, which we don't have to choose. So these are the weights. In the initial epoch, initially in the beginning of the training process, the model or algorithm just guesses them. But as the training continues, right, the algorithm will calculate these weights. So these are the weights that are optimized, right, so that our penalty or the cost function goes to 0. Okay, so what are the total number of parameters here? Okay, let's say we have a 3D filter, right? So 3D filter is how many? So if let's say 3 by 3 by 3 filter, you have 3 is a 9, 9 is a 27, right? 27 weights, 27 parameters here, right? And you have 10 filters, so 27 times 10. Plus you have for each of this filter, you'll have a bias term. So 27 times 10 plus 10, you have 280 parameters. See, this is again another beauty, right? Remember, if you remember the dense layers, the total parameters to train are typically very, very huge. With the convolutional networks, the weights are very, very small. So your model size, are going to be much, much smaller than if you use the dense layer. So more benefit in terms of capturing more hierarchical, transitional, invariant patterns, right? The convolution layer can capture. At the same time, the computation is not that costly, because the number of parameters to train are small. And now if you come to pooling layer, there is nothing to learn, right? Because you just put the pooling filter here and you're just going to take the maximum value of the original input image in that portion. So there's nothing to calculate. There's nothing to train for a pooling layer. So the total number of parameters to train in a pooling layer is 0. Okay, so now we know how pooling layers work. But the real question is, why do we even need them? See, convolution layers was all about learning localized patterns. Patterns that are once learned can be used at other parts in the image, like learning edges, texture, shapes, and thereby building richer representations layer by layer. Pooling layers, on the other hand, serve a completely different purpose. Their main goal is to reduce spatial size, make the model more robust to small shifts, and help it focus on what features actually exist rather than their exact pixel location. Together, both convolutions and pooling are what make CNNs extremely powerful and highly efficient. If you found this video helpful, again, this lesson is part of my Deep Learning Mastery course in Udemy, where I walk through these ideas step by step in more detail and apply them in hands-on projects. If you are a structured learner, I would strongly recommend you to check out the link for the full course in the description below. This video is again part of my Deep Learning Foundation series. The playlist also I have linked in the description below. Thank you so much for watching the video. Happy learning.